Welcome everybody back to the Ithaca Fest. Today we have Dario Stein from Radboud University in Nijmegen, who's going to talk to us about random variables and categories of abstract sample spaces. Dario, you have half an hour and then it will follow 10 minutes question time. Please take it away.
Wonderful, thank you. So yeah, I would like to talk about two different formalisms for doing probability theory, categorical probability theory. One of which is Markov categories, which are maybe well known at this point, and the other one is the more classical approach to probability that you see if you open a probability book that uses the notion of random variable. So the talk is structured like this. I will start a bit with Borel probability and what random variables are. And then there's two lines of work, and the first line of work has been done by Alex Simpson, who developed a very nice formalism called probability sheaves to kind of explain what random variables are for a category theorist. But then it's possible to generalize Borel probability to all sorts of more exotic abstract probability theories. So Markov categories has been a nice language to do that. And with this talk, I want to compute sort of the push out of these two things. So in this talk, I'm going to talk about generalized probability sheaves, which is something that we can create out of every Markov category that has suitable structure, and thereby generalize this amazing work that Alex has been doing. So let's get going. We'll do a little refresher on what a random variable is. So on top here is a statement, like we could see in any probability book, X and Y are independent standard normal random variables. Then the probability that X is bigger than Y is 1/2. Okay, this statement is true, but there's quite a bit to unpack here. So if you really de-sugar what that means in mathematical notation, is first of all, random variables are functions out of a thing called a sample space. This is a measurable space with a probability measure on it, and all the random variables go out of the same sample space. And what the exact nature of this sample space is, this is kind of what I want to talk about. But yeah, so if we make the statement, it means we assume there exists the sample space omega in the background, and then X and Y are not values, they are functions out of the sample space, in this case into the reals. They are measurable functions. The reals are equipped with their Borel algebra. Okay, then we translate the other assumptions about these variables. So then we need to speak about the laws of these variables. Those are the push forward measures of this probability measure on the sample space onto the reals. In this case, they are Gaussian, but don't need to worry about that. So there's a formula like this. Then we encode independence. Independence means that the probability of certain events A and B can be written as the product of probabilities of the marginals. And then we can state what we mean with probability of X being greater equal to Y. This is the probability of this event set, so the set of all omega which are in the background on the sample space, such that X of omega is greater equal to Y of omega. And that is equal to 1/2 in this example, but it's just an example. So you see, when we use random variables, it's on one side very intuitive, but there's actually a lot going on behind the scenes. And as computer scientists or category theorists, we should get kind of to the bottom what's happening behind the scenes. So let's summarize. What's nice about this random variable formalism? Well, random variables can be manipulated just like values. Even though they aren't, they are really measurable functions, but there's somehow a language of using them that lets us use them just like values. All the measures that we talk about, so these probability expressions, they're constructed implicitly for us in the formalism by taking push forwards from the sample space to what we care about. There's a close connection with functional analysis, which is maybe why they are so popular in mathematics. So if you know LP spaces, then we can do functional analysis immediately with the notion of random variable. When we write X equals Y, this is a certain notion of equality that is very easy to express in this formalism, which is equality almost surely of random variables. Conditional expectation is nice because the conditional expectation of a variable is another random variable. It's not a distribution. So in order to even state this, we kind of need random variables. And of course, this nebulous sample space is around, but all the dependence on it is implicit, which we could say is a nice thing. But let me go to the next slide. It's also a bad thing. So what is awkward about random variables is, again, the dependence on the sample space omega is implicit. What is it? Why does everything work? It's kind of ethereal, and I'll get to that. But there's other complications. So the whole formalism, if you're learning it or if you look at expressions in it, doesn't look very type safe. So we can use random variables as if they were numbers, but sometimes we also use them like random variables or like distributions. So for example, if we stuff a random variable into the expectation operator, we get out a number. And then we can make expressions here like the definition of variance, which is x minus expectation of x. Okay, that is a random variable minus a number, which gives a new random variable. So we can take its expectation. And it gets even worse if you get into conditional independence. So the second expression here, I don't know if you can see my cursor. Yeah, you should. The second expression here is actually a number. So this is the expectation of x conditional on y equals y. The type of this expression is number. But this here is a conditional expectation. The type of this is a random variable, which is the random variable y plugged into this function. It gets confusing quickly if we care about type safety. It would be nice to have a formalism that kind of can represent these operations. Also, whenever we want to construct distributions explicitly, the random variable formalism doesn't really help us. To talk about equality in distribution, so two variables have the same law, but they're not equal almost surely, that's a bit more awkward. And conditional distributions, because they are distributions, they are not variables. Again, this is difficult to express. So we kind of want to find a formalism that has the best of both worlds, but we need to answer some questions. And I think Terry Tao really formulated this at first in a blog post where he says we need to clarify what the formal status is of the sample space omega, because we assume it's just there, but then on the fly we can create new random variables that are, for example, independent from everything before it. So we kind of enlarge the sample space while we go in order to allocate new random variables. How can we show this is all consistent? How can we make up new things on the fly? These questions can be answered, and we'll get to it how it can be done. So what we want is a kind of convenient setting for random variables where we don't need to track measurability or sample spaces explicitly. We faithfully include Borel spaces, and we have a dedicated object of random variables, RVX, which contains random variables valued in the space X. And we want to reason about this by some sort of higher order logic. So how could this look? We would like to have operations like this. So we would like to show that whenever we have a measurable transformation from X to Y, then we can transform a random variable into X, into a random variable into Y. So we can post-compose random variables with functions. We would like to show that a random variable of pairs is the same as a pair of random variables. So random variables are these Cartesian values. We want an operation law, which has this type. So it takes a random variable of type X to a probability distribution of type X. If you know the Giri monad, this is exactly what's going on here. And then with this, we can formulate stuff like independence of random variables, which should be a relation, a predicate between the random variables. We can define this tilde, which is often used informally, but it just means the law of this random variable is this certain distribution. So here it will be this formal object. We want to define expectation of this type, conditional expectation, which, as I've said, takes a random variable and another random variable and produces a new random variable. And then we want to have logical statements like, for every random variable that I have and a distribution, I can make a new random variable which is distributed according to that distribution and independent of what I had before. So those are the kind of the way I would want to use this formalism. Can we make it true? Yes, we can, and Alex Simpson did it. So he came up with a Boolean topos, which satisfies all these desiderata. So we have this object of random variables, and I will go briefly over how this construction works so that then later we can generalize it to Markov categories. And this topos consists of probability sheaves. So what's a probability sheaf? You first need to talk about sample spaces in a kind of categorical way. So this is all his story so far. I will get to the new part later, but I'm trying to reproduce it here kind of nicely. So we define this category S. They call the category of sample spaces. Objects are sample spaces, so some Borel space and a probability measure. And a morphism of sample spaces is a bit of a sophisticated object. So it's kind of a measurable function, which takes the probability measure here to the probability measure there under push forward. That's this f star p equals q. So it's a measure-preserving measurable function. But we need to refine it a bit. So we want to take equivalence classes of these measure-preserving functions up to p almost sure equality. Okay, that turns out to be the right definition to give us a category of sample spaces. And what's the interpretation of a morphism? So these morphisms of sample spaces that we described, they're a bit like surjections. So a prototypical example is this. We have a sample space that is a product of two things, x cross y, and then we take the morphism that projects out the y and just gives us x. It's this projection-like thing where we lose information. Or if we have a sample space with a larger sigma algebra, we can restrict the sigma algebra and kind of have less information. So these morphisms are sometimes called coarse graining. So we can think of them as projections. So now what we want to do is take first pre-sheaves on this category of sample spaces. So a probability pre-sheaf is this. It's a functor, it's a contravariant functor on sample spaces to sets. So what is the idea? These elements of the pre-sheaf, they are now some sort of object that varies with the sample space that is defined over all the different sample spaces. And the functorial action means if we have one of these projections of sample spaces, we can let it act on the element, but because of contravariance, it means we can extend the element. If we have it on a small sample space, we can extend it and see how it would look on a larger sample space. So, and then, I mean, the way these toposes work is everything that we define will be equivariant under this enlarging operation of sample spaces, which is what Terry Tao talked about. Now, the sheaf or the pre-sheaf that we're interested in is random variables. How do we set this up? We say for a given space V, we define this functor random variables of type V as follows. If we're given a sample space, then a random variable over that particular sample space is a measurable function. That's the ordinary maths definition. Up to p almost sure equality. That's good to do. And the extension action is just composition. So that's a very, very natural definition. It's almost like a representable pre-sheaf here. And yeah, we can write all these kind of operations that we want to do with random variables, so post-composition with functions, or taking their law, and we'll see that they will be natural transformations, so equivariant with respect to this enlarging of sample space. Then what's really nice is that we can show that each random variable's pre-sheaf is actually a sheaf. So it satisfies some internal coherence conditions. And in particular, it's a sheaf for the atomic topology on this category of sample spaces. What does that mean? It means that, so atomic topology means any morphism of sample spaces is a cover that reflects that these morphisms of sample spaces are like projections or are like surjections. So to say that this is a sheaf, what it means in brief is if we have two random variables and we see that they are equal on a larger sample space, they must already have been equal to begin with. So these restriction operations are, well, this is a separateness condition, and then the other part of the sheaf condition tells us the opposite. So if we have a random variable on a larger sample space, when does it actually come from a restricted sample space? And these things turn out to work rather nicely. And this has to do with the structure of this category of sample spaces, which is what I want to talk about now. So, so Alex calls a square in the category of sample spaces independent. So this is a commutative square. We have essentially 4 random variables here. We call it independent if f1 and f2 are conditionally independent given the diagonal morphism, given the composite here. So that's a bit of a subtle definition, but that takes this notion of conditional independence, which is really central in probability theory, and puts it as extra structure on the category. So the category is now equipped with this notion of some squares are distinguished, some squares are independent, and it's by this condition. And then we can even say when such a square is an independent pullback, and that's an independent square which satisfies the pullback property with respect to other independent squares. So it's a terminal independent square. And then, he postulates 5 axioms that we can say about these independent squares and independent pullback squares, IP1 to IP5. They are stuff like every span can be completed to an independent pullback. And those are one way of capturing how conditional independence works with random variables. And the nice thing is that we can tie this back to what it means to be a sheaf. So following our equivalent for a probability pre-sheaf, namely that F is a sheaf for the atomic topology on S, and that F turns independent squares in S to pullback squares in Z. So if you've seen nominal sets, I'll get to that later. There also a sheaf condition is equivalent to a pullback preservation condition. And here these independent squares are exactly the right kind of structure. So being a sheaf for the atomic topology is demystified here in the sense that we understand it has something to do with preserving independence. So that was the summary of part 1, the work that Alex has been done. So random variable formalism can be formalized very nicely in sheaves over sample spaces. And the ingredients that we want out of the category of sample spaces are that we can take the atomic topology there, and they have this structure of independent squares and pullbacks that satisfy some axioms, which is very rich. And now we ask 2 questions. So first, can we replicate this whole story synthetically? How much of measure theory, how much of Borel probability do we need to prove all these things? Or can we find an abstract categorical proof? And if so, can we generalize this? Alex came up with a bunch of other sites which morally work similar. They all have the same structure. So they have a notion of independent square, independent pullback, which has something to do with probabilities, with surjections, the opposite of injections. But where does this come from? Is there a unifying theory where we input a notion of probability theory and we get out these sites? This is exactly what I will do in the next part. So now comes the generalization from Borel probability to first Markov categories, and then we'll replicate this Borel story for an arbitrary Markov category and talk about sample spaces there. So Markov categories by Fritz are a recent axiomatization of categories of stochastic maps, which are really quite successful. They are very general, and the basic pieces of structures. It's a symmetric monoidal category that has copy and deletion maps. The deletion maps are natural, so it's a semi-Cartesian category, but the copy maps are not natural, and that captures that there's really a difference between doing a random thing twice versus doing a random thing only once and then copying the result. But then those are the basic pieces of structure in which we can formulate quite a lot of probability and related things. So models of these are various flavors of probability, but also relational non-determinism or fresh name generation, or even aspects of ring theory. This is a really nice formalism. What I need in terms of basic definitions are some stuff that can be expressed categorically, which are usually probabilistic concepts, right? So I've talked about determinism. So we call a morphism F deterministic if it commutes with the copy map. That's not automatic. That's exactly like, it isn't always true. So we make it into a definition. We say those morphisms that commute with copying, we call it deterministic. We can also capture P almost sure equality. So if P is a sort of state or a measure, which I draw here with the triangle, then F and G are equal relative to P or P almost surely if those two graph-like distributions here are equal. So whenever something is relativized modulo P, then you should think of this P being here attached to the bottom, and we talk about equalities of these graphs. And there's a concept called conditionals in a Markov category, which here I've shown a small instance of, which is Bayesian inversion. So Bayesian inversion is a way of writing down Bayes' law, this reversal of information flow that we can do in probability, where it's for every distribution and every map F, it's possible to find a converse, which is written F dagger P, which has this property here. So that kind of undoes F. And instead of taking a forward evolution, we can use this to evolve probabilistic processes backwards. So this is the basic language. And now we can use it to replicate the story of probability spaces and sheaves over this Markov category. So if C is the Markov category and we assume it has conditionals, then I define that a probability space is this. It's a pair of an object X and a distribution or a state P on it. And what's a morphism between XP and YQ? There's two different flavors of it. So the first category, which I would call the probability space, we just say that a morphism is a P almost sure equivalence class, again, of morphism X to Y, which takes P to Q. But remember that the morphisms in the Markov category do not need to be deterministic. So here, those maps are per se not deterministic. We can take the subcategory of things that are deterministic, or to say this formally, we now need to say that F is P almost surely deterministic, which is the equation at the bottom. Again, you show, does F interact with, does F preserve copying, but there's a P at the bottom. So this is F being almost truly deterministic. And this forms the category S of C, so sample spaces of C, which are these pairs, and this notion of map. And we can say all sorts of nice things about these categories. So both P of C and S of C are semi-Cartesian monoidal. They are not Markov. Probability spaces P of C have a dagger functor on them, which is given by Bayesian inversion. So this F dagger here really becomes a functor, which we can use to not invert, but retrodict morphisms. There's a nice characterization that says a morphism is P almost surely deterministic if and only if F composed with F dagger is the identity. So the deterministic morphisms are dagger co-isometries, if you like this way of looking at it. And then we get this idempotent F dagger F, which plays the role of conditional expectation operators. So there's quite some nice stuff known about these P of S and P of C. But how can we make a site out of it for random variables? Okay, so we need to define what independent squares are. And that definition is possible to do abstractly. So we say a square like this here is called independent if the following equation holds here. So we can reconstruct F1 and F2 kind of from the composite pH. And if there's any way of reconstructing it, then the reconstructing maps must be the daggers, G1 dagger and G2 dagger. So this equation may or may not hold, and if it holds, then we call the square independent. And that turns out to be a good notion, so we can...
Mano,
Sorry?
produciendo qué? Claro.
Okay, so then we can wonder if for this notion of independent squares, we have independent pullbacks, and we do, and they can be described as follows. So this is called a relative product in probability theory, right? If we have omega 1 p1, omega 2 p2, we can form a product of these states over Q, which is also given in terms of the daggers. And yeah, I can show that squares of these form are precisely the independent pullbacks in S of C. And then we replicate the story abstractly. So we define the sheaf topos that works. We define a pre-sheaf of random variables. This is what you expect, but using the abstract notion of P almost true determinism. And we show it's a sheaf, and that goes through. We can show a bunch of stuff like that. It's Cartesian, that goes through. The only point where I'm stuck is so out of 5 axioms that Alex has written down for independent pullbacks, I can show 4 of them. The 5th one is open. So if anyone wants to have a look at it, and this is the property here. So if we put two squares next to each other, and the big square is independent and B is a pullback, then is A independent. If you think about what that means, that's a whole lot of desugaring with these daggers and equations. I don't know if it's true. I really hope it is. But the nice thing is large parts of the theory already go through without assuming that. It would just be great to see that this axiom is true in general with Markov categories. And I want to end with trying to understand these categories of sample spaces that we get from Markov categories a bit better. And here's a nice way to understand them, which as far as I know is new. So if we have a Markov category and we want to understand what S of C is, well, the really nasty thing is that we always deal with these P almost sure equivalence classes of morphisms, and that's a bit annoying. But we can make a simplifying assumption. So we can call the sample space XP faithful if on it, so with respect to P, almost sure equality is the same as actual equality. So morally, those are spaces that have full support. There's no kind of extraneous stuff that isn't covered by the probability distribution. And this can be made precise as following, and this is really nice. So the following are equivalent. A sample space is isomorphic to a faithful one in the category P of C. This is actually equivalent to a stronger thing, namely that a sample space is isomorphic to a faithful one in the category of sample spaces. So this is saying that isomorphisms, whenever we have them, must be almost truly deterministic. And we can prove that abstractly. And both of these conditions are equivalent to saying that S, so this faithful sample space, is what's called a split support for P. So if we have a notion of taking supports of distributions in an appropriate Markov category sense, then we can hope for this. So then we can ask, is for any sample space, can we find one that is faithful, that is isomorphic to it? And in all common examples, except Borel probability, we will have this. So then we can cut down the whole theory to faithful sample spaces and study those. Now I need to go a bit quick, I think. But the characterizations will be really nice. So for finite probability, sample spaces is a set and a probability distribution. And then we can figure out that this is faithful indeed if the probability distribution has full support. So we can cut down to this. We can consider the category where objects are X and a P, that is non-zero. Morphisms are stochastic matrices. And if we then insist that those morphisms are deterministic, what we're left with is this category fin prop, which has been described. So their morphisms are surjective functions which preserve the probability in an appropriate sense. If we do the same story for relational non-determinism, it's even simpler. So a sample space is a set equipped with a relation, and that is faithful if and only if the relation is everything. So we can forget the relation, and we just need to talk about a set and what's a deterministic relation which maps the total relation on one space to the total relation on the other one. It's a surjective function. So sample spaces induced by relational non-determinism are equivalent to finite sets and surjections. Even more interesting, if you know what Gaussian probability is, I will not do this in detail, but you can see it on the slides. So a Gaussian distribution is given by mean and then a positive semi-definite covariance matrix. But these things up to isomorphism, they can all reduce to identity covariance. And at the end, sample spaces over Gaussian probability are just this. Objects are a Euclidean space, and morphisms are matrices which satisfy this condition. A transpose is the identity. So those are Euclidean co-isometries. That's a very simple category, and somehow to understand Gaussian probability, we just need to understand that. And lastly, we can do the same story for name generation, which is a Markov category. There we show that every faithful sample space is isomorphic to a space of the form k-fresh names and taking its orbit. So sample spaces of name generation are equivalent to the opposite of finite sets and injections. And here, there can be no category theory talk without a Yoneda lemma somewhere. So that's what's going on. So to summarize, we could replicate this whole development of probability sheaves starting from just a Markov category with conditionals. We define synthetically the category of sample spaces, and we get really rich structure on it from completely general considerations. Also, these sample spaces, if we study them up to equivalence, they give us very simple known categories like surjections, injections, op, and so on. So we recognize all of them, and I hope there will be a cool way of studying, say, Gaussian probability over a sheaf category like this, over isometries, which, if you know nominal sets, again, this really looks like a generalization of nominal sets to a kind of continuous setting. I'll end with a bunch of questions. So we've seen that sample spaces of C or probability spaces of C can have a really simple description up to equivalence. If we know it, can we recover the Markov category C from it? Then on this topos of probability sheaves, we get a monad which models variable allocation. So this becomes a Markov category on its own. What is the relation to the original Markov category? And the last one is a question from Arthur Pazinia that he asked, and I can state it very easily now. Namely, we know P of C is a dagger category. Is Bayesian inversion the unique dagger on this? This is something he has been working on, and I think it should also be cleared up. Thank you for your attention, and give me questions.
Right. Thanks very much for the talk. All right, so we started 5 minutes later, so also the next talk will start 5 minutes later at 45. So we have time for questions. Does anybody have any?
Yes,
feel free to unmute yourself. Fosco?
I have a question. It will sound like a comment, but I promise it's a question. The failure of your IP4, I think it was the, or the, probably it's true, but you don't know, it's still open.
Yeah.
So clearly this is true for pullbacks because of like cancellativity is true for pullback, but for a specific reason that they are morphisms in the arrow category of your ambient category that also have a universal property. They are the Cartesian morphisms. So they are part of a factorization system on your arrow category. Maybe if IP4 is true, it's for a similar reason that you can find a way to factor every square in the arrow category with something followed by an independent pullback, pullback, or an independent square. Have you tried to work that out? Is it fails, or you didn't think about it?
I mean, I remember the proof is a thing where you have like 9 daggers everywhere and try to cancel them. So I think at some point you just need to do some technical stuff.
Okay.
Yeah, so I'm not sure. I mean, the axioms for independent pullbacks were chosen, so indeed they mirror some of the properties that pullbacks have automatically, but just with respect to independent squares.
Yeah.
I don't know. I could prove more properties than these axioms, which are also mentioned in Alex's paper, which hold automatically. It's just that I think there's something about IP4 that just needs details, and maybe it needs an extra assumption on the Markov category. Maybe not. Let's find out.
Okay.
By the way, can you ask what is the intuition on this IP4 property, like in terms of probability?
I'm not sure.
Okay. Are there any other questions in the meantime?
I have a small comment. So I think I saw a paper. I will mention one, but I'm not sure that it's the one I'm gonna mention. The title is A Nominal Approach to Probabilistic Separation Logic. It came out in 2024. But that's to say there are some papers where they already try to replace the usual nominal topos with other topos of probabilistic flavor. And indeed, they also mention epic maps. Like the sites is actually very similar to yours. So I wanted to ask you whether you were aware of it.
I was not. Thank you very
Okay.
much.
So
Oh yeah, also. So references are this three papers by Alex, and then this kind of Markov category stuff that was done by Paolo and Tobias and others.
So I will put the title of the one I mentioned in the chat. I will write it. Give me a moment.
All right. Any more questions in the meantime?
Yeah, maybe related. Is these nominal sets has a presentation in terms of continuous group actions? Did you think about presentations like that for these toposes?
No, it would be great. Like especially these isometries. I mean, this is such a simple thing. I think I need a master student or something to look at this.
Yeah, thanks for a nice talk.
Okay. Any more questions or comments? All right. I might have a long one, but maybe let's wait until the very end of the talk, so I don't want to take up so much time. Let's thank our speaker again.